I'm going to briefly demonstrate how to use a digital experiment, that is, a simulation that allows one to make measurements, collect data, and analyze the data. In this case, equilibrium reaction at high pressure, where hydrogen and nitrogen react to form ammonia, and the pressure and the temperature and the feed composition can all be changed. Here's the link to the simulation on the LearnChemE site, and here's a snapshot of what the simulation looks like. We can feed hydrogen, nitrogen, ammonia, control their flow rates with these mass flow controllers, control the pressure, this pressure controller, control the temperature in the reactant, as a catalyst in a reactor in this heater. And then we open a valve for helium that we can, by switching this valve, take a sample, inject it to a GC, and we'll get a readout here for the composition of the equilibrium mixture. And so the idea we're treating these gases is ideal, but at high pressures, that's not going to be a good assumption. But in terms of demonstrating the concepts, it works just as well, but is less complicated if we use ideal gases. So let's look at this simulation. So here's the digital experiment where we can open the valves. In this case, I'll open the hydrogen and nitrogen valves by clicking, and then I can set flow rates. So these are mass flow rates. So if we're going to run somewhat close to stoichiometric, we obviously need a lot more mass flow rate of nitrogen. We'll have to, of course, run stoichiometric. We can also feed ammonia. I won't for just the demonstration. We can increase pressure, and high pressures are important to push equilibrium to the right, where we're reacting 4 moles to form 2 moles. So going to high pressures. You can also raise the temperature, which will make the reaction faster, but will also push equilibrium to lower conversions because ammonia formation from hydrogen and nitrogen is an exothermic reaction. I can open the helium tank, which is used to run the gas chromatograph. You'll notice it say the system is reaching equilibrium. And now it says it's ready, so I can click on this switching valve. And what it will do is inject the sample into the GC. And then it gives us the output, the mole fractions of hydrogen, nitrogen, and ammonia at these conditions we picked. I can click on the valve again to get back so we can take another sample, and then we could certainly change the pressure. So let's go up quite a bit in pressure. The industrial reactions run at quite high pressures to get good equilibrium conversions. Let the system reach equilibrium, and certainly we sped this up relative to a real physical system so we can take more data in a reasonable amount of time. Now I can inject again a sample into the GC, and it's running through the GC. And again, we sped this up. It could take 15, 20 minutes. You notice now the mole fraction ammonia is 0.59 instead of 0.50 previously because we pushed equilibrium to the right at the higher pressure. So this is an example of a digital experiment. We have a worksheet that describes details of what measurements should be made and what things should be calculated. And we have some brief directions here also. The idea here is that we're looking at chemical equilibrium. So we're assuming the reactor residence time is long enough that we reach equilibrium by the time we leave the reactor.